Okay, now we start for real. So yesterday I showed you guys that we were going to be working on problem B1-C. B is for Calc BC. This is problem 1 that we're doing. C indicates that, and I should have said this yesterday if I didn't, that you get to use a calculator for this problem. And I'll try to go through it pretty quickly so I don't use too much of your time. You can always rewatch the video. So the idea is this. We have a certain rate. This is a piecewise function. For the first 300 seconds, the rate of people getting onto an escalator is given here. Okay, after 300 seconds, no one is getting on. Okay, as people get on the escalator, they also exit the line at 0.7 people per second. And so you could think of this as a function, e of t equals 0.7 t. And initially, there are 20 people in the line at time t equals 0. So right away, I'm thinking this is probably a net change problem. So let's go ahead and see how this works out. The first question is very basic. How many people enter the line during the time interval from 0 to 300? Okay, so I'll show you my worked out solution. So realize if you graph a rate curve, and that's what we're given this rate here. If you were to graph the rate curve and find the area under it, think about the rectangles. Okay, the height might be in people, the units would be in people per second. The base here, number of seconds, you multiply those two together and you'll get number of people. Okay, and so what we're trying to do is find the area under the curve from 0 to 300. And really, don't forget, this is a calculator problem, and so you're going to enter this into your calculator. I'd advise writing this as y1, and then just taking the integral from 0 to 100 of y1 with respect to x. Okay, and so it gives us 270 people. Okay, realize that that's all the way from 0 to 300, and no more people are getting on after that, or getting in line, or whatever this is. Okay, and then part B. How many people are in line at that time? This is the net change part of the problem. Okay, the people in line are the people that we started with plus the change in people in that time. Now the change isn't just this first part. Okay, this is people getting in. We can't forget that people are leaving. And so this part right here is how many got into line. This is how many people exited the line. And so if we calculate that, the initial amount, the amount in, the amount out, we get the answer to part B. Okay, part C. And now we're getting a little more complicated. And don't forget, I did warn you that initially these problems are going to be a little frustrating because they cover everything we've done all year. That's why we've had to hold off on free response problems until now. Okay, so now we want to know, at some time, is there a time in which there are no people in line for the escalator after t equals 300? And what is the first time that that would occur? Okay, so remember, we started with 20. A maximum of 270 got on, and then you're subtracting a certain number of people. Okay, and so if you look at our solution to part B, we're going to use that now. At t equals 300, there were 80 people. After that, people are just leaving at the rate of 0.7 people per second. And so you're just asking yourself, well, when would 0.7 people leaving per second add up to 80 people? Okay, and so if you look what I've done here, we're looking for the time at which it occurs. And so remember, we started at 300 seconds. And then we're going to multiply 80 people times 1 second per 0.7 people so that the units reduce, and we'll find the number of seconds it takes for those 80 people to leave, and we get our answer there. Okay, realize if they don't tell you, round to 3 decimal places and include the units. Okay, now for the difficult part. Okay, so when would the number of people in line up to 300 seconds be at a minimum? So think about that. Okay, think about what that means. A minimum, we're probably dealing with a derivative of some sort. Okay, and so if we make our new function, the function that we used at the end of part B, the total number of people in line would be the initial 20. Okay, the change, now this is from 0 to any time value under less than or equal to 300. Okay, the net change right here, and then of course minus the people leaving. So this function is the number of people in line at any one time. If you were to graph this, you'd get a curve, okay, and it would reach a minimum at some value. And as long as it's a continuous curve, a differentiable curve, the derivative at that minimum would be 0. So basically, this question is asking, when is the derivative of that function equal to 0? And we're going to derive it term by term. The derivative of this constant is simply 0. Okay, the derivative of this integral, that's something we really have to recognize. That's a fundamental theorem of calculus problem. And it's actually very simple. And we'll do that in the next step. The derivative with respect to t of that term is simply negative 0.7. Okay, so the derivative of the integral, okay, these just undo each other. They're inverses. And so we get the rate function out. And so this equals r of t, which is the original function they gave us. Okay, and minus 0.7. And so my question is when is this derivative equal to 0? Don't forget, you already entered this as y1, and you want to use your calculator to evaluate when it is equal to 0.7. Okay, now you actually get two different answers on your calculator. T equals 33 and 166. And so what you want to do is find the number of people at those times. So evaluate the number of people at t equals 33 and t equals 166. See which one gives you the minimum. The minimum number of people in that time was 3.8, kind of silly, but the time is what they're interested in, at 33 seconds. All right, so I understand that that kind of ended in a very difficult way. Rewatch the video as much as you want. Ask questions when we have office hours, but your next problem that I want you to try to work on is B2N. The N stands for no calculator on this one. Good luck, everybody.